Hello, everyone. Come on in. Anybody have any questions while we wait? All right. Well, it's 5:20 now, so I guess I should stop waiting. Actually, I just remembered I forgot to tell this to my face-to-face class, but basically, I want to let you guys know y'all didn't do as badly as I expected on the midterm. Not to say anything bad about you, it's just every semester, your first midterm uh, turns out to be quite low compared to the online tests. And of course, I always expect that, but your class actually did quite a bit better than I expected in that respect. But still, I do this just about every semester. And what it is the midterm counts as like 20% of your course grade, and the final counts as like 25% of your course grade. So those are the two tests that you actually have to take proctored in some way and showing your ID. So I know exactly who's taking the test and all that good stuff. And that first one, the midterm, often is lower because the students are not quite figuring out, the difference between learning and just being able to look up stuff really well. So this is usually the first shot over the bow to warn them about that. So what I do for my students is I don't tell them this until afterwards. So don't tell anybody if they're going to take me. But basically, if they actually miss or do poorly on the midterm, if they make a better grade on the final, I'll replace their midterm grade with their final exam grade. So you guys are, you've got a high homework grade, a high conceptual homework grade, a high online test grade, a pretty high lab average. Chances are your grade's looking really pretty good right now. Probably A, B, something like that. And then this midterm came along, and it's looking maybe not so A, B-ish anymore because you did lower than you expected and way lower than you've been doing on the online test. So what I'm saying is that's okay. We've learned we need to learn. We learn we need to learn more and do less looking up. And we got to figure out how to do better. And I was telling a student today, for instance, it's not unreasonable, even after you finish your homework problems that are assigned to you from a given chapter, to do, say, at least 30 more homework problems, evenly distributed amongst the sections within the book. So if you have like 5 sections, I would say after you finish the homework that was assigned to you, you should probably be considering trying to do 6 questions from each section of each chapter. So that's sort of a very reasonable amount. My goal was always shooting for doing all of the odd problems at the end of the chapter. I rarely made it, but I always came within, probably 70 to 90% of all the odd problems. So that's another goal you can shoot for. But really, at the end of the day in physics, that's all that really makes you do better is your ability to solve a bunch of problems. And solving problems is not the same as looking at people solving them and then regurgitating that solution. You don't learn anything from that. You learn some, but not much. So like when it comes time for you to do a problem, you usually can't get started or something like that. That's a very common result of seeing people solve problems without banging your head against the wall for a little bit to make a way to figure out how to solve the problem yourself. So it's much more valuable to take pokes at how to solve the problem, then look at the answer, close the answer, or look at the answer. If your answer is right, great, you pat yourself on the back. If your answer is not right, then maybe look at the solution a little bit, see what's different, what's alike to what you did, kind of analyze a little bit, then close that solution and try to solve it again. And if you get stuck, stop, go look at the solution, close the solution, and try starting over. Maybe you can start from where you are, but it might be better to just start right over again. So you got to do a little bit more of that, a lot more solving of problems. So the main thing is, like I said, this midterm grade, if you didn't do well or you didn't do as well as you'd like, don't worry about it. You can make it up by doing better on the final. So the other thing that bothered me is that I did find that some students never even took the practice final. That's really bad because one student that I talked to that got the highest grade of any of my classes, I looked and that person had taken the practice test over 20 times. So that's really, that equates basically to doing that, all the odd problems in the back of the book at the end of each chapter or something like that. That's that kind of level is really what we need to do. So the online practice tests are a lot easier way to do that than going through and doing all the solutions in the odd questions in the back of the chapter. But I prefer the book way. A lot of students prefer the other way. So just find something to do a lot more problems with. And again, look at examples to get ideas, but then close examples and try to solve the problem on your own. All right. Anybody have any questions? I'm still letting students in. I'm getting ready to kill off chapter 9 for us. I just posted 2 videos from my YouTube channel about chapter 9, and it sort of shows you why chapter 9 covers conservation of momentum and then also covers center of mass, which seem like totally distinct different problems, but they're not. So you'll see in that case, I have a train car with a cannon in it and a stack of cannonballs all on the same side with the cannon. And every time the cannon fires, the whole train car recoils, like we learned about recoils and shooting rifles and stuff like that. So the train car recoils with some small velocity because it has a huge mass and the initial momentum of the whole system was 0. But now we have a small mass, the cannonball, with a huge velocity going, say, to the right. And the recoil is the huge mass going to the left. And then you say, okay, well, it's going to do that. And it's going to go at that constant velocity for the amount of time that the ball will travel until it hits the other side. So you take into account the relative motion of the train car relative to the cannonball, and you can calculate how far the train gets before it hits the wall, because as soon as it hits the wall, conservation of momentum is going to make them both come to a stop the way I've got the train set up. So with that in mind, after 1 cannonball, you can tell exactly how much the train car's moved. After 2 cannonballs, you can do the same process, 3, 4, 5, doesn't matter, as many cannonballs as you want. And that'll all be from conservation of conservation of linear momentum. You can figure out how far the train car's moved. But you could also do the same problem by calculating the center of mass of the system, which would include the train car, the cannon, the cannonballs all initially, and then the train car, the cannon, the cannonballs all at the end when all the cannonballs are stacked on the opposite side. And because that's a closed system, basically all the forces acting on it are internal. The center of mass of the system has to stay in the same place. But if you calculate the center of mass as if, say, the origin is the left side of the train track, the train car, and calculate where all the balls are, where the train, where the cannon is, and where the train car is, you can calculate a center of mass, and that position will not move. So in order to correct for that, you're gonna have to make the new center of mass be there, and lo and behold, it gives you the exact same answer. So it's even that complicated to explain. So you can imagine why I didn't actually work it in real time for you guys, but I did offer both videos. So check those out. I think that's an excellent example of conservation of momentum and center of mass calculations. One more time before I get started, anybody have any specific questions they'd like to ask me? All right. Well, last time we talked about conservation of momentum, we had talked about one-dimensional collisions, basically head-on collisions that were conserving conserving momentum and conserving kinetic energy. In other words, they were elastic collisions. So in that case, we actually found this nice little result that VA minus VB is equal to negative parentheses VA prime minus VB prime close parentheses. So it's basically like the relative velocity of A to B just reverses with the relative velocity of B to A from before the collision to after the collision. And that was true independent of what their masses were and stuff like that. But now we can continue to use that equation to find out specific final velocities of other types of head-on collisions. I'm going to do that, and I'm going to do basically something equivalent to problem 40, or at least in the 4th edition, it was problem 40 in chapter 9. So I'm going to do something equivalent to that, and then I'm going to do a couple two-dimensional collision problems so we can see how they work, and we'll even consider one of them being elastic. So let's go ahead and get started. I'm going to start by sharing my screen. Anybody again have any questions before I get cracking? Okay, let's see if this is working. Looks like it's working so far. All right, so what we found before was basically if you had a mass A moving with a velocity VA, and actually let me do something that A looked really bad. So if you had a mass A moving with velocity VA toward a mass B moving with velocity VB, then after the collision, you had a mass A moving with velocity VA prime and a mass B moving with velocity VB prime. That was that. I mean, that's, and basically we said momentum was conserved, and that gave us PA VA plus PB, plus MB VB is equal to MA VA prime plus MB VB prime. And we had that for the X direction. So you could just multiply the VAs times, well, actually it doesn't matter for the X direction because it's one dimensional, I forgot. So you had that, and then you had the conservation of kinetic energy that said 1/2 MA VA squared plus 1/2 MB VB squared is equal to 1/2 MA VA prime squared plus 1/2 MB VB prime squared. If we got all the VAs, VA and VA prime, in other words, on one side of both of those equations, and the VB and VB prime on one side of both of those equations, then we could actually divide these one with the squares by the other one. And when we did that, we ended up getting this nice result that VA minus VB is equal to the negative of VA prime minus VB prime. So that is a nice equation we can use. Now what I'm going to do is let's consider a stationary target. Again, this is a head-on collision for a stationary target. In this case, that means VB is equal to 0. So 1 becomes VA is equal to negative VA prime minus VB prime. But we also have conservation of momentum. So I'll call this equation 2, and that's going to be MA VA is equal to MA VA prime plus MB VB prime. So if I solve equation 1 for, say, let's say VB prime, so VB prime, which notice if you distribute that negative, the VB prime on the right-hand side is actually positive. So this is going to just equal VA, and then this VA over here is negative, so it's going to add to the other side and make it VA prime. Yep, that's right. So I'll call this equation 1 prime, and I will plug it into equation 2. So I'm going to get MA VA is equal to MA times VA plus VA prime. Oops, wrong one. Stop to pay attention for a second there. That's VA prime. Plus MB. Now here I'm going to plug it in. This will be VA plus VA prime. So now what I'm going to try to do is distribute that, but get all the VA primes together. So I'm going to have a MA VA is equal to MA VA prime plus MB VA plus MB VA prime. So I can now see that basically I have a MA on the right-hand side. And when I pull the MB VA to the left-hand side, that'll be a minus. So I'll write MB, so MA minus MB, and all that times VA. That takes care of this term, and that takes care of this term. And then on the other side, we've got MA plus MB. Both of those times VA prime. So that gives us VA prime is actually equal to, and this is a new formula that your author tells you don't need to memorize because it's so easy to derive. And he's absolutely right. I would definitely recommend you deriving it. But there's another reason too. Maybe someone will notice this. Does anybody recognize the form of this multiplier that I have written so far? This MA minus MB over MA plus MB. If you didn't, it seems like no one does. That's actually the same form as the acceleration in the Atwood machine. The Atwood machine had MA minus MB over MA plus MB, all of that in parentheses times G to give you the acceleration. So it was like a dimensionless quantity multiplied by something with the dimensions that you want. So the something with the dimensions that you want was G because you wanted A. And the dimensionless quantity was in fact the same thing, MA minus MB over MA plus MB. So yeah, that's a really nice expression. And now we can use the result about VB, specifically 1 prime. So 1 prime gives us this neat little expression. VB prime is equal to VA plus VA prime, which is MA minus MB over MA plus MB times VA. So now I'm going to go ahead and get a common denominator. I'm going to say this is MA plus MB over actually, let me write this a little further along. Since I'm getting a common denominator, I'll just write one big denominator there. And I'll put a fraction here. And that's the numerator for the VA term. Now I'm going to say plus. Now the numerator for the for the other VA term, that's going to be MA minus MB. And of course, both of these are multiplied by VA. So I'll just put the VA like that. Now you can see what happens. The MB and the MB cancel out and we end up getting 2MA, which also is kind of interesting. So we get 2MA over MA plus MB times VA. So VB prime, the velocity of the target, is just 2MA over MA plus MB times VA. Does anybody recognize this dimensionless quantity here? The acceleration for the Atwood machine was MA minus MB over MA plus MB times G, and the tension was 2MA over MA plus MB times MB times G. So you see, we actually get two things that look very much like the Atwood machine results. So yeah, your author's right that you shouldn't have to memorize it because this derivation was pretty straightforward. Remember how I got that first equation 1 that I wrote up there that became 1 prime. Y'all should be able to derive that as well. That was just that neat little trick that V VA squared minus VA prime squared factored into VA minus VA prime plus VA prime. That allowed us to cancel some stuff out, allowed us to get rid of the masses and all that stuff by dividing those equations, and ultimately gave us that result 1. So remember, that's an important result as well. Any questions on that one? So that's just the algebra used in deriving stuff, but it's a pretty, straightforward process. For instance, if you had, let's say you had a cue ball hitting a 8 ball. So in other words, so on a cue ball hitting an 8 ball, you say a cue ball is rolling at, let's say 2.00 meters per second to a head-on collision with an 8 ball. Sitting still. What will be their final speeds? Now, since it's an 8 ball and a cue ball, you can assume that MA is equal to MB is equal to just plain M. Okay, so that's kind of nice. So let's do our solution. So A is going to be our cue ball, just to keep our wits about us. And B is going to be our 8 ball. So V cue ball prime has got to equal MA, which would be M minus M over M plus M times VA. And this, of course, is 2.00 meters per second, but you can tell that's going to be 0. Now the 8 ball, V8, V8 is going to be 2 times M over M plus M times VA. Again, VA is equal to 2.00 meters per second. But you can see 2M over 2M is just 1. So we're just going to get 2.00 meters per second. And this is exactly reminiscent of Newton's cradle. I'm sure you've all seen Newton's cradle. You don't necessarily know what that word means or what that phrase means, but that's Newton's cradle is basically a little rack like this. And it's got a bar here and a bar here, and they got a string attached to a ball, and then another ball with another string attached, and another ball with another string attached, and another ball with another string attached, and finally another ball with another string attached. And if you pull out one ball, then out will pop one ball on the other side. So it's just a changing of the velocity. So the ball comes in that you lifted with a velocity V, say equals 2 meters per second. And on the other side, one ball pops out with a velocity being 2 meters per second because it almost goes the same height as the first one did. So that's basically all that shows. So that's a simple example. Now let's do it for the less general case. This is, like I said, this is sort of like problem 40 from chapter 9 and the 4th edition of the textbook, where they ask you to do this. But I'm going to go with the same sort of stuff, but I'm not going to assume VB is equal to 0. Okay. So let's just assume target is not initially sitting still. But it's still one-dimensional. It's still conservation of momentum's acting, and it's still an elastic collision. So we already know equation 1 is that VA minus VB is equal to the negative of VA prime minus VB prime. Okay. Now we also have that other crazy thing, conservation of momentum, that tells us MA VA plus MB VB is equal to MA VA prime plus MB VB prime. Okay, so that's equation 2 as well. So that's just conservation of momentum, which is part of what this equation 1 came from. But again, just like I did last time, I'm going to eliminate one of the final velocities, and this time I'll do it again like I did last time. I'm going to eliminate VB prime by solving for VB prime in terms of VA, VB, and VA prime. So from equation 1, I can see that VB prime is going to equal, notice on the right-hand side, VB prime is technically positive because it's a minus with a minus. So that time is going to be positive, and then I have negative VA on the right. It comes to the left and becomes VA prime, and then plus VA, and then minus VB. So basically, I've looked at this equation exactly in the mirror so that the right-hand side became my left-hand side, and its left-hand side became my right-hand side. So this is now equation 1 prime, say. Now I'm going to plug 1 prime into 2, just like I did before. Okay. So I'm going to say MA VA plus MB VB is equal to MA VA prime plus MB. Now I'm going to write VA prime plus VA minus VB. Okay. Now I'm going to work out this left right-hand side a little bit. That's going to give me MA VA prime plus MB VA prime plus MB VA minus MB VB. Okay. Now it would be super, super smart of me to group all of the VA primes together. And in fact, I can do that by saying MA plus MB factored out times VA prime. And I can say, I'll just leave it like this for right now, and I'll rewrite the whole equation in a second. Okay, so now I want all the VAs together. So I'm going to take that second term on the right and bring it to the left. And that's going to give me MA times VA is now going to be MAVA minus MBVA. So I'm just going to factor out the VA and write this as MA minus MB. Oops, I miswrote VA. And that's going to be multiplied by VA. That takes care of that term and that term. Okay. And now I'm going to pull this term, the third term on the right-hand side. I'm going to pull that to the left-hand side. Notice it's a minus on the right-hand side. It's going to become a positive on the left-hand side. So it's going to become plus 2MB times VB. That takes care of that term and that term. All that is going to be equal to MA plus MB times VA prime. So I can now solve for VA prime. And VA prime is going to be equal to, notice it'll be MA minus MB over MA plus MB times VA plus 2MB over MA plus MB times VB. So that's the general answer for any head-on collision that you have that's elastic. Now that I have VA prime, I can use my expression 1 prime to find VB prime. So VB prime, this is from 1 prime, VB prime is equal to VA prime, which we just decided was MA minus MB over MA plus MB. And I'm writing in green all of a sudden. Okay. Plus 2MB over MA plus MB times VB. So that's just the first term because VB prime said it's equal to VA prime, which I just wrote, plus VA. So instead of plus VA, I'm going to go ahead and get a common denominator and say MA plus MB under MA plus MB times VA. And then it says minus VB. So again, I'm going to get a common denominator and I'm going to do MA plus MB over MA plus MB. Now you got to remember here, this fraction bar is actually basically like parentheses. So that means you got to distribute that negative sign as well. So you got to be careful with that. Now I can group this term right here that has a VA. I can group that with this one. And I can group this term right here that has a VB with this term that has a VB. So I'm going to rewrite it all, and I'll go back to my original color because I don't know what I did in the first place. So we're going to say VB prime is now going to be equal to, now I have originally MA minus MB. And now the other blue term is going to be plus MA plus MB. All that, of course, is going to be over MA plus MB, and all that is multiplied by VA. I think you can see already that the negative MB and the positive MB cancels out. So that gives me that. Now the other ones, the two red ones that I put up here, they're going to be plus 2MB. Now, remember, I said I got to distribute this negative, so I'm now going to have a minus MA and then a minus MB. And then, of course, that's still over MA plus MB, and then times VB. Now, in this case, you see that the 2MB is going to be subtracted, have a minus MB subtracted from it, so that's just going to be MB minus MA, in fact. So now we can finally write VB prime is equal to 2MA over MA plus MB times VA plus, now we're going to have MB minus MA over MA plus MB, all that times VB. And that's it. That's our general, completely general solution for two colliding head-on collisions for an elastic head-on collision. Any questions on that? So if you'll notice, these two equations and these two equations that I had here, or these three equations that I had here, I think only the very first one at the top of this page, that one I called number one, I think that's the only one that's really numbered. So technically your textbook author and me do not want you using the second equation on this page. We don't want you using the third equation on this page. We don't want you using the two equations on this page either, because they're not numbered. So they're not ones that you're supposed to have on your sheet. But I just showed you how to derive them. I would highly recommend you derive them maybe twice even. And when you derive them, you'll probably remember them forever. If not, then you just commit them to memory. But notice it's definitely still that same scenario, MA minus MB over MA plus MB, and then 2MB over MA plus MB for the VA. Notice that the 2 times the mass term always has the same subscript as the velocity term it's with. So when you do the VA, you're going to have the difference with the VA, but when you do the VB prime, you're going to have the difference with the VB. But the other one's the 2. So this is pretty straightforward to memorize. I would say I've never committed it to memory except maybe for a test, but I've never committed to memory since then because it's pretty quick to derive, as you hopefully saw there. So that's basically it on those one-dimensional problems. Anybody have any questions on that?
Which equation are we supposed to start from? The one that we're supposed to have on our sheet.
Yeah, you should start with equation 1 that I have written up here. I'll circle it again. Now, you should also derive that equation, which I showed you how to do that in the last class that was recorded. But you should be able to get that one. So I do that as a first start. And then using that, and as you saw, I just used conservation of momentum in equation 2 that's on this page. I was able to derive all this. So it's not that many lines. You can see it's not that bad, but give it a try. And in fact, if y'all want to, if y'all do the derivation of all 3 of these, in other words, that number 1, the VA prime here and the VB prime here, if you do all these, I'll give you extra credit. So derive that guy, and that guy for extra credit. Okay, you just turn that in. I'll try to remember to put an assignment spot on this week's module. If I don't, just send it to me by email, but I'll probably try to remember. I'll probably remember, hopefully. Okay, anybody have any questions on that? If you use this, if you solve probably 10 problems like this using this formula, you're going to have it memorized too that way. So deriving it is one way. This is just like also, I never forget the quadratic formula, specifically because I took the time to learn how to derive ax squared plus bx plus c equals 0. In other words, I learned how to complete the square on that with just symbols a, b, and c. And that's how you actually get the quadratic formula. And now I will never forget negative b plus or minus square root of b squared minus 4ac over 2a. So that's the same kind of thing. It's just a wonderful skill to have. That doesn't mean everybody has it. That doesn't mean everybody should have it. But I'm saying I suspect everybody can do it. If you can get through Calculus 1, I think you can get through all of these derivations. So anyways, any questions before I move on? All right, I'm going to go to a conservation of momentum problem in which it's 2-dimensional, okay? So let's imagine, I'm going to say a proton, no, let's say a pool ball. Is traveling at 3.00 meters per second and collides with a resting 2 ball. they both leave, making a 45-degree angle with the pool balls original trajectory. Whoa. The two ball below and the pool ball above. What are their final speeds? Okay. So solution. So conservation of momentum, summation p sub I x is equal to summation over I p sub I, or p, or excuse me, over f. Actually, I should leave that way. I'll call it 0, and summation over I p sub x final, like that. Okay, that's what conservation of momentum in the x direction means. So in this case, all we have is the mass of the pool ball, which I'll call m sub p, times 3.00 meters per second is equal to m sub p times vp prime cosine 45 plus m sub 2 v sub 2 prime cosine negative 45. That's what I meant by above and below. Okay, now the good news is MP is equal to M2 is equal to M. So I can go ahead and cancel out all of these masses. Okay, now after the Y component, summation I of P sub I Y 0 is equal to summation I of P sub I Y final. This gives me 0 is equal to MP VP prime sine 45 degrees plus M2 V2 prime sine of negative 45 degrees. So I'll call this equation 1, I'll call this equation 2, but I'll also realize that the masses cancel out on that one as well. Any questions on all this so far? So from equation 1, from equation 1, I can see that 3.00 meters per second is equal to, now notice the cosine of 45 and the cosine of negative 45 are actually identical. And the way I usually know this is I just look at the trig functions when they're graphed. And that's what y equals cosine x looks like. So you see it's a mirror reflection about the y-axis. So the negative is the same as the positive. So I can basically say that VP, oops, I shouldn't write that. I can say that VP prime cosine 45 plus VP or excuse me, plus V2 prime cosine 45 have a common factor of 45. So that's 3.00 meters per second is equal to cosine 45 times VP plus V2 prime. So that's may or may not be that helpful. But now that I look at 2 gives us something even more helpful, because I also know that sine looks like this. So I can now say that 0, I don't know what happened there. I can say that 0 is equal to VP prime sine 45 minus V2 prime sine 45. Okay. And that gives me that VP or V2 prime sine 45 is equal to VP prime sine 45, which means obviously those don't matter. And that means V2 prime is equal to VP prime. So I'll call this equation 3. So combining equation 3 and 2, I get basically, or excuse me, 3 and 1, not 3 and 2. Yay. What the heck just happened? Okay. That's not the right one. Okay. Well, that scared me. I don't know what happened there. Sorry about that, folks. Oh, old people like us, we shouldn't be allowed stuff. So in equation 1, what we ended up finding out was that the 3.00 meters per second was equal to cosine 45 times VP prime plus V2 prime. Well, now I can just call them both V prime, and I'll say that 3.00 meters per second equals cosine 45 times 2V prime. So V prime is actually equal to 3.00 meters per second divided by 2 times cosine 45. And I do not like how this V turned out, so I'm going to rewrite that. So V prime, which equals VP prime, which equals V2 prime, is going to be equal to, this is where a calculator would be really awesome to have right now. Oh, I did not bring my calculator. So, never mind. I have this. I'm going to do 3. I'm going to do 2. I'm going to do 45 cosine. Yep. And now I'm going to multiply 45 cosine times 2. And then I'm going to divide 3 by that. And I get 2.12. So that's it. That's the answer. And it's actually both answers. Any questions on that? Okay, let's try another one then. Yeah, we got plenty of time. So let's say now a proton is headed toward a helium nucleus at, let's say, 2.00 times 10 to the 5th meters per second. And the proton's mass is 1.01 times U. That U, by the way, the easiest way to remember that is just 1 over Avogadro's number, and then you move the decimal 3 places because Avogadro's number is about grams and this is about kilograms. So that's a nice way to remember that. So this is M proton. The helium nucleus was at rest and its mass is M alpha is equal to 4.00 U. Okay, that's another name for the helium nucleus. It's called the alpha particle because it's basically 2 protons and 2 neutrons. And that was one of the first historically small particles to be discovered was the helium nucleus. They didn't know it was a helium nucleus at the time, but they named it alpha. And then, of course, the second one they found turned out to be an electron. They named that beta. And the third one they found, they called it gamma. That turned out to be a photon. So we got that. I want to check something real quick. The proton, actually, we don't know that. One particle leaves this elastic collision at 53.1 degrees above the proton's trajectory. I mean the initial trajectory, of course. Okay, so what we have here is the conservation of momentum problem. And what we have basically is 1.01 U times 2.00 times 10 to the 5th meters per second. That's all in the X direction. In other words, this might seem like we're reducing this to a very certain type of problem, a very special problem, but it's not. You can always take the initial velocity of the two things, which might actually be moving towards each other or away from each other, doesn't really matter. But you can always find a frame where one of them's sitting still. And as long as they're both going parallel / anti-parallel to each other, you can treat that direction as an x-axis. You're completely free of doing that, and you're completely free to adjust your coordinates so that one of them's sitting still. And that's perfectly general. It just, you'd have to change it back to the proper coordinate system once you, which is the lab coordinate system when you're finished with it. So with no loss of generality, I'm pretending that the proton's initially moving along the positive x-axis. Okay. Now that's going to result in one of the masses moving at, I could have sworn, let me hold on a second, folks. Let me double check something here. I'm trying to do a problem that I solved earlier, but I forgot some of the details. and I'm changing some of the numbers too. So let me double check something before I make a big mistake. I hate to make a big mistake. Hopefully this won't take as long as I think. All right, we got plenty of time anyways. Okay, what I want. Okay. That's what it was. Sorry about that. I'm not doing a helium nucleus. I'm going to do a proton. That way we can't tell, and that makes it life a lot easier. Plus, it gives you the same mass. So let's do this. I'm going to scratch through helium nucleus and say a proton. Okay. Proton. I'll call this a target proton. The target proton was at rest, and I'll just cross out all this and put a period right there. Yeah, that works. Okay. So all the particles have a mass of 1.01. That's the key point, and that's going to get rid of it. And that allows me to do some stuff that I think still allows you to see a lot of algebra that's necessary for you guys to observe so you can learn how to solve this stuff. So let's go ahead and work with that now. So this one we have a 1.0. Whoa. Back to my blue color. We have a 1.01 U. That's the mass again. Times V, we don't know which one, so I'll just call it VA prime times cosine of 53.1 degrees plus 1.01 U times VB prime cosine of just plain theta. That's the angle we don't know at all. We want to find all this information out. Okay. So I've got that one equation. Let's call this equation 1. And let's say equation 2 now is conservation of momentum. So, or excuse me, conservation of momentum in the y direction. So in this case, I'm going to have 0 is equal to, and notice, by the way, these 1.01s did cancel out, so we don't have to have that anymore. I will have 0 equals, again, the m's are going to cancel out, so I'll just leave it off. I'm going to say VA prime, dang it, VA prime sine of 53.1 degrees. And actually, that's supposed to be a lowercase a. Plus VB prime sine of theta. So that's equation 2. And then because it's elastic, I also have a third equation. And that is 1/2 1.01 U times 2.00 times 10 to the 5th meters per second squared is equal to 1/2 1.01 U times V A prime squared plus 1/2 1.01 u times VB prime squared. That's going to be equation 3. Okay, so now we've got 3 unknowns. We don't know VA prime, we don't know VB prime, and we don't know theta, but that's exactly what we can solve. Okay, so in fact, to make it a little easier on me, I'm going to change this to just plain VA. Actually, I'll make it just plain VA, the capital A. Okay, just so I don't have that symbol to deal with. Notice also that the 1/2 times 1.01 canceled out with all 3 of these terms. So we've got a pretty nice expression there. And this, of course, is VA prime, or excuse me, VA as well. So I can take, for instance, yes, I will take the second term in equation 1 and bring it over to the left. So from equation 1, I'm going to have VA minus VA cosine 53.1 degrees is equal to VB. Whoa. I hate when it does this. Is equal to VB, and that was supposed to be a prime, by the way. It's equal to VB prime cosine 50, or excuse me, cosine theta. And now in equation 2, I'm going to have VA prime sine 53.1 degrees equals the negative of VB prime sine theta. And now I'm going to take this equation 1 and I'm going to square it. So I'm going to get VA squared minus 2VA VA prime. That really should be a lowercase a there, by the way. So that VA prime there times cosine. God dang it. And then plus VA, excuse me, VA prime squared cosine squared of 53.1. Running out of space. All right, what I'm going to do, since I ran out of space there, is I'm going to go ahead and write this below it. So let's do it this way. 1 squared. That's going to give me VA squared minus 2VA VA prime cosine 53.1 degrees plus VA prime squared cosine squared 53.1 degrees is equal to VB prime squared cosine squared theta. Equation 2 squared is going to give me VA prime squared sine squared 53.1 degrees. And that's equal to VB prime squared times sine squared theta. Okay, so let's call this equation 3 and this equation 4. I'm going to add 3 and 4. Okay, so what you can see is when I add 3 to 4's left-hand side, I'm going to get a VA squared from the first term in 3 minus a 2VA V lowercase a prime cosine 53 0.1 plus, now here's the weird part, you got a VA. That was supposed to be a lowercase a here too, by the way. This thing is supposed to be a lowercase a. Okay. So when you add these two, this VA prime squared times sine squared theta plus VA prime squared times cosine squared theta, it's just going to give us VA prime squared. That was the whole purpose in doing this. Okay. So that's the left-hand side. The right-hand side, you can see, is going to be VB prime squared cosine squared theta plus VB prime squared sine squared theta, which is just going to give us VB prime squared. So that's kind of nice. We've actually got stuff that we can use here. And in fact, yeah, that gives us VA prime squared and VB prime squared. Okay. So this equation right here says number 3 here says VA squared is equal to VA prime squared plus VB prime squared. So that could be kind of helpful. We can actually get rid of VA squared and replace that with VA prime squared plus VB prime squared. So plugging in, let's say plug in 3. Oops, that was not supposed to be 3. I had already used 3. Let's make that equation 5. Okay, plug 5 into that guy. That's going to give us VA squared right here. The very first term is going to be VA prime squared plus VB prime squared minus 2VA VA. Oops, those are supposed to be lowercase 2. Dang it, why do I keep doing that? Same thing here. VA prime cosine 53.1 degree plus VA prime squared is equal to VB prime squared. So you can see already that this VA prime and this one are going to add to give me 2 VA. So 2 VA prime squared. And this VB prime squared is actually going to cancel out with this VB prime squared. So I got 2 VA prime squared minus 2 VA VA prime cosine 53.1 is equal to 0. So that gives me 2 VA prime times VA. I might go ahead and factoring on the fly minus VA cosine 53.1 degree is equal to 0. So that gives me that VA prime it's got to equal VA cosine 53.1. So VA, remember, is at 2 times 10 to the 5th. And I'm going to say 53.1. And y'all should probably know what that is. It should be 4/5 or 0.8. Excuse me, 0.6. So this gives me 1.2 times 10 to the 5th. Okay. And now we can use, I'll go over here just to not write it on a separate page because then I have to copy back and forth stuff. So I'm going to say what we found was that VA prime squared plus VB prime squared is equal to VA squared. So VB prime, this was supposed to be lowercase a again. Okay, so what that means is that VB prime is equal to the square root of VA squared. That's supposed to be the uppercase one finally. You can't believe it. Just stop it now. Supposed to be VA squared, and then I erased everything. It's going great. Minus VA prime squared. So if I take that 2.00 squared minus 1.20 squared and just multiply it by 10 to the 5th, that should give me my right answer. So 2 squared obviously is 4. And 1.2 squared should be 1.44. Subtract that. That gives me 2.56. Take the square root of that. That gives me 1.6. So this is equal to 1.6 times 10 to the 5th meters per second, or let me write it in blue. VB prime is equal to 1.60 times 10 to the 5th meters per second. Box it off in red. So that's another way you can solve it. And that's the main thing I wanted to show you for the conservation of momentum is just how to solve a couple of conservation of momentum problems using all the algebra and stuff like that. You can tell I probably am a little more comfortable working with symbols than I am with numbers. I just find that I make a lot of careless mistakes. Well, obviously you see I make careless mistakes anyways, but I make a lot more careless mistakes when I'm working with numbers. So that's why I reverted to using VA. But this is a nice trick. We basically took got all the VAs on one side and VBs on another side, squared it for the X equation, squared it for the Y equation as well after you got them on separate sides, because then it was one term on each side. And then used the squared from the kinetic energy to simplify things. And once I added the two equations, making use of sine squareds plus cosine squareds being equal to 1, I was able to solve it. So this method will work over and over and over again if you're consistently given one of the angles and none of the final speeds. Okay. Any questions on that? We've got about 8 minutes left. I wanted to just reiterate something. Anybody have any questions? Okay, so I did want to show you a little bit more about the center of mass. So if you have a bunch of particles, the center of mass, we talked about this before, would be the mass of one particle times the x of that particle plus the mass of another particle times the x position of that particle plus ... And then you divide it by the total mass like that. And then the y center of mass is the same thing. You'd say m1 y1 plus m2 y2 plus ... over m1 plus m2 plus ... Again, for however many terms you have, and you can put the origin anywhere you want. And I think that makes sense if you just think about putting a bunch of masses on a ruler. Obviously, not only does the ruler, if you're trying to balance the ruler with your finger under the 50 centimeter mark, if you put a 1 kilogram mass 1 centimeter away, that's going to be about 1/10 as bad if I put 1 kilogram mass 10 centimeters away, right? So you see that the distance from a particular point to where you put the force is really important. That's why I have to multiply the X times the M. Also, if I put a 1 gram mass versus a 1 kilogram mass, obviously the kilogram is a much bigger effect. So that's why it's M times X. And then just to get it back into units of centimeters, you have to divide it by what mass? Well, none of them make sense except for the total mass. So that's a neat way of looking at it. If you're doing non-discrete things, in other words, you're actually looking at matter as if it's continuous, not made up of little atoms, which you pretty much can because atoms are really small, like on the order of infinitesimal. So you can actually generalize this to XCM equals the integral of x dm over the integral of dm, or YCM is equal to the integral y dm over the integral of dm. So just imagine, for instance, this is y axis here, and that's the x axis there. Let's imagine a triangle like this. Let's say this triangle has a height h and a width w, and I want to find the center of mass. Now, the rule is basically it's 2/3 of the way. That's the ultimate result we'll figure out, but it's always 2/3 turn towards the fattest end. So I'm going to go from the light end, which in left and right, the right hand side is the heavy end. So I expect this center of mass to be 2/3 W. And similarly, if I go from top to bottom, the top seems to be the light part. So this is going to be 1/3 H. That's where I suspect the center of mass to be. So let's calculate it. X center of mass. So first off, I'm going to say, well, I need to figure out the X center of mass. I need an integrand X that doesn't vary very much from one side of DM to the other side of DM. So that means I'm going to choose a little sliver like this, say. And the thickness of this, of course, is just dx. But the height is the actual y. Well, I can tell that the equation for this is clearly y equals mx plus b, where b is 0. So this is going to be y equals h over w times x. So now what I know is the integral of x dm is just equal to the integral of x. Now my dm is going to be basically, excuse me. I might as well do that too. The integral of x, which is like that. Now dm can be, in this case, I'm going to treat this like a two-dimensional homogeneous lambda. So we're going to say it's got a density sigma times d area. Okay. Well, that little rectangle I just drew is my area. And that, of course, has a width x and a height y, which is h over w times x, and then times a sigma, or excuse me, not a width x. We can get that x out of there. A width dx. Okay, and times a sigma, which we don't know right now, and now I made that dx really too small. So times dx like that. So I'm just going to integrate this from x equals 0 to w. And what I'll get is, notice this is sigma h over w times the integral of x squared dx. That's going to be sigma h over w times 1/3, since I'm integrating from 0 to w, 1/3 w squared, or w cubed, excuse me. Okay. Now the integral of dm just has to be everything without that x that I had before. So this is going to be the integral of sigma h over w x times dx from 0 to w. And in this case, you get sigma h over w times the integral of x dx. That's just going to be 1/2 w squared. So now if you take xcm is equal to the integral of x dm over the integral of dm, you're just going to get sigma h w cubed over 3w divided by sigma h over 2w times w squared. Obviously, that's going to cancel out one of those. That's going to cancel out one of those. That sigma is going to cancel out. That h is going to cancel out. And ultimately, I'm going to get a 2/3. Now I've got a w squared left up here and a w to 1 power here. So that's 2/3 w, which is exactly what we expected. So that's it. You guys are free to go. If you want to, you can try the Y one. You do the same thing, only you're going to have to find, obviously it's a little different. I'm going to work it here before I shut off the camera. The time is exactly up right now. You're free to stick around while I do the last part, or you're free to go. I'm just going to go ahead and work out the YCM and explain it as I go. Anybody have any questions before they do split? All right, let me calculate the YCM then. So the YCM. Well, the integral of ydm, in this case, I'm going to make it go like this. Okay, so this part right here is just a height w, if you will. And then this thickness here is dy. But this distance right here, down here, that's sort of a whole different function. In fact, that's the x as a function of y. So this actually turns out to be x equals w over h times y. So this side should ultimately become y times sigma dA, which is equal to sigma times the integral of y. Now our dA is supposed to be w minus w over h times y times dy. Because notice the top of that is w and the bottom of that is the inverse of the function that we had earlier, because now we've got to solve it for y instead of for x. So that's the actual difference there. And I've got to integrate this from y equals 0 to y equals h. So this becomes sigma. Now the first one is y times w times dy. So I'm going to say y times w, the integral of that is going to be w over 2 h squared. Because it's the integral of wy, which is 1/2 wy squared. And then I evaluate that at h and I evaluate that at 0. So that got rid of that part. Now the other one's going to be a minus. Now it's w over h, but it's y times y, so that's y squared. The integral of y squared is y cubed times 1/3. So I'm going to put a 3 down here in the bottom, and then I'm going to evaluate that at h. So that's going to be h cubed. And that should be it. Now I just got to do the math. Obviously, one of these h's will cancel out, leaving a 2. And now I have w over 2 h squared minus w over 3 h squared. The least common denominator is obviously 6. So that's going to be 3w minus 2w h squared, or I should say 3w h squared minus 2w h squared, which would be WH squared. So I'm going to get, I'm going to get sigma times WH squared over 6. Okay. Now the integral of dm is going to be the same thing. I'll put the sigma out here. Now I'm just going to do w minus w over h y dy from 0 to h. That's going to give me sigma. Now the integral of w is just going to be w times y evaluated from h to 0. So this is just going to be wh. And the integral of negative w over h times y is going to be 1/2 y squared. So this is going to just become h squared like that over 2. So again, getting a cancellation here, this h cancels out with that, leaving 1. I've got a wh minus a 1/2 wh. So that's a 1/2 wh. So this is going to be sigma wh over 2. So YCM is supposed to be the integral of ydm over the integral of dm. Well, the integral of ydm we found was sigma wh squared over 6. And this one we found was sigma wh over 2. That's obviously going to be 2 over 6. A lot of cancellations going on here. This sigma cancels out with this. This w cancels out with that. This 2 cancels out with that. So I get 2, 6, just plain h, which of course is 1/3 h, just as advertised. So YCM is equal to 1/3, or excuse me, 1/3 h. That's it. Any questions about that, guys? You'll see I've done other ones on my YouTube channel. I'll put some links up here to those, but they're not too complicated. You can make them more complicated if you want. Instead of, notice that density, I just use that density, which is really the sort of the mass per unit area, that sigma that I used. That's a mass per unit area. I could make that equal to some constant times x squared if I wanted to. And then that would soup things up a little bit. And that would be basically a triangle that got heavier the further you got to the right. And then the answer wouldn't come out to be 2/3. It'd probably be more like, 7/8 or something like that. I also gave my students the opportunity to do a calculation of the center of mass of the Earth-Moon system for extra credit. So you guys can do that too. So calculate center of mass of the Earth-Moon system. So what I mean by that, the easiest way to do this is you just imagine a coordinate system like this. This is my y-axis, or this is my x-axis, this is my y-axis. And you put the Earth centered there, okay? Now, it helps to know the radius of the Earth, because ideally you want to find out what this result is in terms of that. So what this means is for the Earth, the m is, I want to say something like 5.9 times 10 to the 24th. So you can look this up yourself, times 10 to the 24th kilograms. Look it up. The radius of the Earth is equal to 6.38 times 10 to the 6 meters. But the position x Earth is going to be 0. And y Earth, of course, will also be 0, but we're not dealing with y at all. And then for the moon, the mass of the moon You can look it up. And its position, X moon, would actually be, it's about 60 times the Earth's radius. 60 times the Earth's radius, but you can look that up too. Okay, and you're going to put it right here at X moon. And then you just calculate the center of mass of that. And what you'll see is that the center of mass is not at the center of the Earth. In fact, the center of mass is the only thing that actually follows an elliptical orbit. And it's a point right about here. I tell my students is roughly 7/8 of the Earth's radius towards the surface. So I estimate this to be approximately 7/8 of the Earth's radius, but you can do the calculation for extra credit. You guys are free to go. I'll wait for the last person to leave. If anybody has any questions, by all means, ask me.
I had a question on chapter 8 homework. I'm kind of confused about the problem.
Okay.
I'm gonna go ahead because I got an answer, and it's kind of I don't know how they got the answer. So
you want to share the screen?
Yeah. Do you want me to share? Yeah. Do you want me to share the screen for you?
Yeah, I just made it where you're able to.
Yeah. Let's see here. Just before. And Chrome tab. Applications.
Grabs a hanging rope and swings over a lake. He releases the rope when his velocity is. Can you show me what that velocity is? Oh, 0. Okay. And the first part of the question, can you show me that real quick? I know you got it right, but I just want to find out what they're working at. So what is the angle theta when he releases the rope? So A. And then part B, what is the tension of the rope just before he releases it? So B, tension equals question mark. Okay. And he gave us the radius of the rope is basically 10 meters, or the length of the rope. Okay. So what you found out was that basically, and you're wanting to know that. So let me go ahead and steal the screen back from you. Okay. So I've written this information down. What we have here is basically an L with a mass on it and a velocity on it as well. And what you know is by conservation of energy, this angle theta brought this height up to H such that MGH, or excuse me, MG lowercase h, is equal to 1/2 mv squared. So that h, of course, is not that helpful in here, but you can tell that this part right here is L times cosine theta. And this is H. So you know that H plus L cosine theta is equal to L. So you can see that H is equal to L minus L cosine theta. I know you've already worked this part, but I'm just trying to make sure everybody follows how we got to this part. So that's ultimately what will allow you to compute cosine theta with, and it also allows you to compute H. And of course, H is equal to H is equal to, if I cancel out the M's, I can see that H would be equal to V squared over 2G. So that's the H, you know that, you know the L, so now you can solve for cosine theta. Easy peasy, right? This is 4.0 meters per second squared over 2 times 9.8 meters per second. So that gives you everything you need for H. And then, like I said, you can plug it in with the L being 10, and that'll get you the theta. Now, this next part they want to know is, what is the tension? Well, once you've got that angle, you can see that the tension has to be this direction. I call it just T. Your book sometimes calls it FT. So that's the tension. And in fact, you could also say that this angle right here is theta. But what has to happen is that T has to be, in order for him to hang at that point and reach a velocity of 0, at that instant, it sort of has to be somewhat in equilibrium. But you see, so the mass there is hanging. We've got this force mg acting downward, and the T cosine theta has to just be equal to mg. Yeah, so you see T cosine theta would be this component right here. And T cosine theta from the summation of forces in the y direction equals mass times acceleration in the y direction. That has to be 0. So you get T cosine theta minus mg is equal to 0. So my thought is that the tension should be equal to mg over cosine theta. And that should be good enough. Because, yeah, at that point, the velocity was 0. Is that similar to what you got, or do you get something entirely different?
Yeah, that's kind of similar. I think I just made a mistake because I did those steps until I got to that point, and I think I did something wrong. I think I put the wrong number in my calculator or something. I'm going over it. I'm looking similar. It looks similar to what I did. It's just I think I messed up one of the values.
What'd you get for the angle theta? Because I know you got that right.
23.
23 degrees?
Yeah, 23 degrees.
Okay, so I took cosine of that. That's 90.9205. I'm dividing it. That gives me 42.6. Newtons. You said it was 23.5 degrees?
23 degrees.
Okay.
Just 23.
Okay, gotcha.
Yeah.
So yeah, I got 42.6. I don't know if that's the right answer, but I don't think I'm missing anything else. You could also, you have to realize that the tension has to be sufficient to, for instance, cancel out the, or provide the mv squared over r force required to swing it, but I don't think that's necessary to go through at this point. So did you try that answer?
Yeah. It said that it was wrong. So
It said my answer was wrong too.
Yeah.
Let me think. Think about this a little bit. I will actually what I'll do is I'll let everybody know. So I'll send everybody some kind of solution on this or something. I just I'm thinking about 2 or 3 different things right now that I might have missed. And I was kind of apprehensive. That's why I said I wasn't sure it was going to be right. But I'll work this and then see if I get the same angle as you. That'll give me an idea that I'm doing that part right. And then I'll write something up and send it to everybody so everybody can see it. All right.
I can do that by tonight because it's due tonight. I can do that by tonight, or
yeah, I'll try to get that done while I'm waiting for this recording to do.
I got you. You have a good day. All right.
All right. See you, man.
Oh, hey, one more question. Well, one more
Yes, sir.
question. Did you get my email with the picture of the work that I did for the exam?
Yes.
All right.
I'm looking at
Yeah,
right now to confirm. I remembered that Joseph sending me something, so I was thinking.
Yeah.
Yep, I got it. Thank you.
Yeah,
sir.
I did most of my I did most of my calculation on a calculator accidentally, and I forgot to write it down. And then I ran out of time because I figured that I wanted to be nice to the time because it was already 75 minutes. So I forgot to write it down, but I did most of it on a sheet of paper. So
that's cool. No problem. Well, thank you, sir.
yeah.
You guys have a
thank
good
you.
one, and I will see you next week.